In part 2 of my Tower Basics series, I'll be talking about buckling. Historically with my videos, I haven't really discussed much of the engineering theory behind these device builds, but towers are very unique in that this single topic is so important it really defines the entire design. I debated on how in-depth to go over the theory as it can get pretty complex, but I decided to keep it as simple as possible and really just focus on how it would apply to Science Olympiad tower building. So what exactly is buckling? Simply put, it's the failure mode of compression. I would say most people have a good feeling for the failure mode of tension, or the pulling apart of a piece. Here is a picture of a nice clean tension failure. You can see that the stick has literally been separated cleanly. With tension, as long as the piece has the same cross-sectional area and density, it will have the same tensile strength regardless of its length. We'll soon find out that that is definitely not the case with compression. Here is a video of me simulating buckling failure by applying compression to a long stick. By holding one end and having the other end stuck on the ground, you can see that even when I apply a purely vertical force, the stick bends in an unpredictable way. Actually, the shape is predictable, but the direction is not. That will be a pretty important concept to remember later on. While I'm not actually breaking the stick in this video, once it starts to bend at all, it has passed its maximum load capability, so if the same load was continued to be applied, it would break. This brings us to the introduction of Euler's critical load definition and formula. The definition is basically what I just demonstrated, the compressive load at which a slender column will suddenly bend or buckle. The formula may look complex and somewhat intimidating, but for our purposes it can be simplified down to a couple key concepts. The first thing to know about how we can work with this equation is that we don't really care about calculating values for the critical load. We really only care about the relationship between certain parameters in this equation. I'll go over what we are interested in one at a time. The first parameter we care about in this equation is E, or Young's modulus. Young's modulus is an engineering property of materials that measures tensile or compressive stiffness. It quantifies the relationship between tensile or compressive stress, force per unit area, and axial strain, or proportional deformation. The example given on this wiki page is that silly putty has a low Young's modulus because it deforms quickly with pressure, as aluminum has a high Young's modulus because it doesn't increase in length much at all. If that's all a bit complicated, don't worry, because if you look at this chart plotting Young's modulus versus density for balsa wood, it's nearly linear. That means for our practical purposes, we can directly substitute material density for Young's modulus, or E in the Euler equation, and we're already familiar with density and how to measure it with a simple scale. The next variable in this equation that we are interested in exploring is I, or the minimum second moment of area of the cross-section of the column. The area moment of inertia is probably a term most people haven't heard of. It's a geometric property which reflects how its points are distributed with regard to an arbitrary axis. For most common shapes, we usually compute this for x and y axes perpendicular to each other. Here is the result for a rectangle. The derivation of this property can get a bit messy, so it's not uncommon to look up the area moment of inertias for common shapes in tables like this. Again, if this is all very confusing, don't worry about it, because for our use case, this can be simplified down quite a bit. I encourage you to explore more online if you're interested. If you go on to study mechanical or civil engineering in college, you will become very familiar with these and other formulas. If we focus on a simple solution, such as a square, you can see that the Ix and Iy values are identical and related only to the side length. Again, it doesn't matter what the values are for our purposes, only that they are the same. If you recall, in the Euler formula, it's the minimum area moment of inertia that is used. That means for our tower legs, given a cross-sectional area budget, it's best to use a square shape so that the buckling strength will be the same in both directions. Okay, back to the Euler equation. I'm about ready to talk about the really important part. First, K here, or the column effective length factor, can be considered 1 and can be ignored for our use case. That leaves us with L, or the length of the column. Nothing fancy, but if you notice, it's in the denominator of the equation and it's squared. What does that mean? It means that if you made the length of your column half as long, the critical load would be 4 times as much. If you were to make it 1/4 as long, it would be 16 times stronger in compression. As you might have guessed, this is a huge key to building strong towers. But before we go building any towers, can we really trust some 300-year-old dude in a goofy outfit? Luckily, the relationship part of this equation is very easy to test and demonstrate. I recommend you try what I'm about to show to prove it to yourself. What I have here is a 60 centimeter stick, and this time one end of it is pressing down on a scale. The key is to try and press down as vertically as possible and to see if you can read the approximate value when the stick starts to bend. Do it a couple times to see if you can get a consistent reading. Here it looks like about 14 to 15 grams. Again, it's not critical to get an exact value. Now I'm going to hold it exactly halfway down, effectively making it into a 30 centimeter stick, and perform the same test. It's tricky to get an accurate reading, but you can tell it's in the 50 to 80 gram range, roughly 4 times greater than before. And finally, now I'm going to hold the stick at 15 centimeters. This time we see values around 250 grams, again roughly 4 times stronger than the previous length. It looks like that old dude actually knew what he was talking about. In all seriousness, this is a really important thing to understand. To summarize, simple material properties like density and cross-sectional area have a linear relationship to critical load, but the length of the column has a squared relationship. In the next video, we'll finally start to build and test some towers to see if what we just learned about buckling applies to our real-world devices. Thanks for watching, and please don't hesitate to reach out to me if you have any questions.